Hello, everyone. Ooh, that's a little loud. I'm Bryce Adelstein Lelbach. Very glad to be here with you today. We have come quite a way. My girlfriend and I came here from the Galapagos Islands because we were in vacation last week. So we've been traveling for about 24 hours, took like 4 flights across 4 different countries. But we're here. And she took this picture while we were there. These are blue-footed boobies. There's 2 adult ones and 1 baby. It has nothing to do with the talk. It's just a nice picture. So here's another nice picture. So I've worked on programming languages and compilers for over a decade. I've served as the chair of the standard C++ library evolution group, which designs and standardizes the C++ standard library. But I'm retired from that job now. I'm enjoying the easy life. So I'm a principal architect at NVIDIA, where I drive our strategy for HPC programming models, C++ compilers, and C++ libraries, and now I do some Python stuff too. So C++20 was the largest release of C++ in over a decade. It delivered 4 major features: modules, coroutines, concepts, and ranges, and dozens of other additions and improvements. And C++20 is now pretty much widely available. Most implementations are shipping most of C++20 in productions, and we're starting to see more and more adoption and more projects and organizations switching to C++20 as their default. And the next C++ standard, C++23, has been out for about a year. And there's a lot of exciting changes coming in C++23. To name a few, there's a bunch of enhancements and additions to ranges, which were added in C++20. And there's formatted output. There's MDSpan, which is a multidimensional array abstraction. It's actually the thing that I joined the C++ committee to originally work on back like 10 years ago. So that's about how long it takes to get a thing into the standard, 10 years. There's expected, a new error reporting paradigm. There's standard library modules and deducing this. And C++23 features will start to become available in your compilers the next year or so. You'll be able to start playing around with these things pretty much anywhere. So in the months leading up to a new release of C++, our focus is often on what makes it into that release and what doesn't, and we tend to put longer-term goals on the shelf. And today I sort of want to dust off some of those longer-term goals and look beyond C++23 at what's next for C++. So I want to tell you about 3 features that we're working on, features that I think will revolutionize the way that we write C++ code. And 2 of them are almost certainly going to be in C++26. And those features are reflection, which is one of the ones that'll be in C++26, pattern matching, and senders, which will also be in C++26. So our exploration today is going to focus on what we can do with these facilities, not the specifics of the committee proposals or the merits of different design decisions. This is really a talk about possibilities, not details. Now, much of what I'll show you is tentative, and in some places a little speculative. In places where the designs are uncertain, I've just sort of chosen the option that makes the most sense to me and ignored the others. And this talk represents my own views. I do not speak for the C++ committee, and no single person really can. So first, we're going to talk about reflection. But to do that, we first have to talk about metaprogramming. So what is metaprogramming? Metaprogramming is the craft of creating or modifying programs as the product of other programs. And reflective metaprogramming is metaprogramming that incorporates data from the program being modified and also might modify the program itself. So there's 3 components to reflective metaprogramming. First, there's reflection, extracting information from the program about the program. Then you have some compile time programming facility, some tools for manipulating that information. And then finally, you need a way to do injection, to insert new programmatic entities based on that compile time logic that executed. So let's look at a very simple example, a function that takes an enumerator and returns its name as a string. And so we're using a few new C++ constructs here. The reify operator takes a C++ entity, that could be a function, a struct, an enumerator, a variable, or even something like a namespace, and produces a reflection. Now, a reflection is a handle to an internal compiler representation of that thing. In this case, it's of the type T. Now, std meta info is the type for all reflection objects. So that _t will produce us a std meta info object. Reflections can be manipulated and transformed just like any C++ objects. So here we pass the reflection of the enum type t to the function meta members of. And meta members of returns a vector of meta infos that represent all of the enumerators of t. Because it's a vector, we can use a range-based for loop to iterate through the elements. And here we want to use the new compile time expanded for loop template for. Each element may be a different type, which a normal for loop wouldn't allow. In each iteration of this compile time for loop, we want to check if the enum parameter of the function is equal to the value of the current enumerator. And to do that, we need to take the reflection of the current enumerator and turn it back into a real entity. We can do this with the splice operator. So the splice operator takes a reflection value, std meta info, and turns it back into the entity that it represents. In this case, the enumerator in question. So if we had a type, a reflection of a type turns into a type. If we had an expression, a reflection of an expression, the reify operator would turn it into the value of that expression. If the parameter is equal to the current enumerator, then we need to return its name. And we can get that name with another function that operates on reflections, meta name of. And that's it. So here's another example, hash append, a hash protocol that incrementally passes input to a hash algorithm. It takes a hasher object and an object to hash. First, we're going to reflect on the object that we're hashing and use the members of function to get all of its members. Now, the members of function takes an optional parameter which filters for certain kind of members. In this case, we don't actually want all the members. We just want the non-static data members. We don't want any function members. We don't want any static data members. Next, we're going to do a template for over all of those data members. And we use the splice operator to access the data member. And we recursively call hash append on the member. Make sense? Okay, now's the fun part. Thus far, we've just been splicing reflections, but in many cases, we need to do more complex code injection, like creating new identifiers for generated methods and members. We can do this with token sequences. A token sequence is a series of unparsed C++ tokens that can be manipulated via metaprogramming and then injected into a program. And the type of a token sequence is std meta info. So a token sequence does not have to be a valid C++ anything. It's just a string of tokens. Like right here, we have a token sequence of C equals. That's fine. So let's look at how we'd implement std tuple with reflection using token sequences. Historically, tuple has been very tricky to implement, requiring thousands of lines of code, but with token sequences, it's a lot simpler. So when manipulating and injecting token sequences, we're often going to use const-eval blocks, which is a new construct that performs const-expr evaluation of some arbitrary code within an arbitrary context, like at class scope. It's somewhat similar to static assert, where you give it something and it evaluates it, and you can put a static assert at class scope or at namespace scope. So everything injected during this const-expr block will be placed in the current context, in this case in the body of the class tuple. And we'll get to how we do that injection in a moment. So first, we get the reflections of all of the types in the tuple using the reify operator, and we stick them into a vector of meta-infos. Then, For each of those types, we create a token sequence with the token capture operator. The token capture operator takes an arbitrary sequence of tokens and produces a token sequence that's stored in a std meta-info. The sequence of tokens is arbitrary except that it must have balanced braces. That is, there must be as many left braces as there are right braces. Parentheses can be unbalanced, but braces have to be balanced, otherwise we wouldn't be able to parse it. So that token sequence will contain a declaration for a data member. We're trying to declare each of the data members of the tuple. And so a declaration of a data member, you have three parts. You have the type, which we have right here. We'll splice it in using reflection splicing. And then we need to give the declaration a name. So we're going to use this /ID thing that I'll explain in a moment to generate a name, and that name is going to be _I, where I is its position in the tuple. So the first element will be _0, then _1, then _2, _3, etc. And then finally we have the closing semicolon that is in the token sequence there. Now we need to inject this token sequence, which we do with Q-injection. So Q-injection takes a meta-info object that represents a token sequence and queues it for injection in the current context at the end of the current constant evaluation. And it has to work like this with a queuing model for reasons I don't want to get into, just trust me. So let's look at a more complex example. We're going to automate writing properties, which are members, data members, that have a getter and a setter method. So our property function will take two parameters, a reflection of the type of the property and the name of the property. So first, we'll create the name of the new data member in the token sequence. And we're going to just create a meta-info object in this local context here with that name. So token sequences can contain interpolations, which produce tokens from strings, expressions, or token sequences. So identifier interpolations take strings, concatenate them together, and produce a new identifier token. In this case, we are creating a token called m_named. The new token is interpolated into a token sequence, and the member variable here will be a std meta-info object that represents the token sequence that contains this newly generated name. Value interpolation creates a token representing the value of a const expression. If the value is a reflection, then the tokens of the reflected entity are inserted. In this case, we are building the declaration of the data member for this property. And so we want to insert the tokens of the variable type here, not the token type. If we didn't use interpolation here, if we just typed type here, then in the injected code, it would just inject the word type instead of the represented type here. Sequence interpolation inserts the tokens that are in a given token sequence. So that means that its argument has to be a std meta-info object. And here we're using it to insert the name that we generated in the line above. And now we inject the whole declaration. So the type of the declared member, the name of the declared member, and finally a semicolon. Okay, next we're going to inject a method called getName. We generate the name here with a string interpolation. And this method is just going to return the data member that we've generated. And then next, we'll inject a method called setName. And it's going to take one parameter of the properties type, and then it will assign that parameter to the data member. So property doesn't return anything. It just queues up things for injection into the current context, and you use it within one of these const eval blocks. So let's take a look at how we'd use it. So let's write a book class which has two properties, title and author, both of which are strings. So this first invocation of property will add a string data member called title, a getTitle function that returns it, and a setTitle function that sets it. And this invocation of property will add an author member, a getter, and a setter. I'm going to take questions at the end, but there are slide numbers here, so if you have a question, you can write down the slide number. So reflection can be a powerful tool for automating data layout transformations and optimizations. One common transformation that can have huge performance impacts is switching between array of structs, where data is stored as a single sequence of multi-component elements, and structive arrays, where data is stored as one sequence for each separate component. Now, switching between these two usually requires structural code changes, which makes it harder. Array of structs is often more intuitive, but structs of array usually offers better memory access patterns, which can be critical when parallelizing or vectorizing. Consider this code here, which implies an operation to just the red channel of a sequence of colors or pixels. So this will have a strided memory access pattern, which in some cases may have alignment issues or inhibit vectorization. So we can use reflection to write a wrapping type that automates transforming from array of structs to struct of arrays. So we've got our reflection type SOA, which takes as single template parameter the thing that we're reflecting on. And the first thing we're going to do is we're going to get the non-static data members of the type that we're wrapping. We did this earlier. We're just called meta members of. Then we're going to inject a vector member for each of the data members of the wrapped type. So we have one stood vector for each of the members of T. Next, we're going to write a constructor for this class, and it will initialize the wrapper from a range of underlying structs, a range of T's, so from array of struct data. Within that constructor, we have a const eval block where we're going to insert the code that will actually implement this constructor. So we iterate over each of the component vectors and inject code to initialize that vector. So for each component vector, we're going to resize it, and then we copy the applicable data from the range of array of structs. So what's happening here is that this const eval block happens at compile time, and then inside of that const eval block, we have a queue injection, which creates these token sequences that can get inserted into this constructor. And those token sequences become real C++ code that runs at runtime. We can make our structive array wrapper object act like a range of array of structs so that it can be iterated in the same way as a range of the original type T. So the elements of this range would be tuples of references to the underlying components. So for example, to write an indexing operator, instead of a const eval block, we build up a comma-separated token, inside of a const eval block, we build up a comma-separated token sequence that will access the ith element of each of the component vectors. And we're going to use this meta list builder utility here, which handles the commas, inserting the commas into this token sequence that we're going to build up. And we can just use plus equals to append more stuff into this token sequence, and then it will add the comma there. Then we use tie to return a tuple of references to those elements. And we're using it in a token sequence, which we're going to inject. And notice how we inject a return statement here. This function wouldn't actually have a return statement otherwise. Now, this works because the const eval block that we're injecting is within the function body. And so that's where this stuff will be injected. not into the class body. So this same approach can be used to create actual iterators, but in the interest of brevity, we're not going to look at that in detail. I think that this is enough to illustrate the general approach. So now we can take our natural and intuitive array of structs code, and by simply changing the type of image from vector to SOA, we've switched the code from array of structs to struct of arrays. And this changes the memory access pattern for our single channel operation from strided access to contiguous access, which is more cache efficient and easier to vectorize. So we go from this to this. So I believe that reflection will fundamentally change how we write C++ code. Reflection will help us solve problems that today often require boilerplate, macros, or external code generation, like serialization, protocol and language bindings, instrumentation, logging, debugging, dependency injection, etc. It will change how we build and design libraries and how we evolve the language itself. This is a giant tortoise, and she moves very slowly, unlike this talk, which is moving very quickly. My girlfriend took this picture. It's a really good picture. Okay, now let's move on to pattern matching. C++ has two selection mechanisms today. Switches operate on a single integral value, which is often too limited. You can't use them with string literals or with objects. If statements, on the other hand, operate on arbitrary Boolean expressions. They're powerful and can express almost anything, but they're often too complex and verbose. We need something in between the two, a powerful but concise way to select and decompose objects. And that's what we'll be getting with inspect, which is a new selection mechanism for C++. So inspect matches values against patterns, and then binds variables when those matches are successful. Now inspect is an expression, not a statement, and an expect expression takes a parameter, the object to select against, and a series of patterns. There's a variety of different patterns available, and I'll highlight a handful of them today. Each pattern is followed by a statement, which is taken if the pattern matches. Inspect stops at the first match, not the best match. So it's the first lexical match. Constant patterns match if the object is equal to the constant. And the wildcard pattern, which is just two underscores, will match against anything. Constant patterns aren't limited to integrals or enums. They can be strings or any arbitrary object. Here's another example, Fibonacci written with inspect. So here we use the identifier pattern, which binds the value to a name. In this case, A. Pattern guards can be used to perform arbitrary tests for a match. Now, since C++ 17, we've been able to destructure tuple-like objects. And we can do that with inspect, too, with compound patterns. So this compound pattern consists of three constant patterns. It will match if the object can be destructured into three components, like a tuple, and if each of those components is equal to the corresponding constant. On the other hand, this compound pattern consists of three variable patterns, so it will match against anything that can be destructured into three components, regardless of their value. Alternative patterns can match different types in variant-like objects, any-like objects, and polymorphic objects. They give us a much cleaner way to work with variants. Instead of writing a visitor and calling instead visit, which is usually unpleasant, we can just inspect the variant and use alternative patterns. We can use alternatives to match a polymorphic object against different classes. Here we have a circle class and a rectangle class. both of which inherit from a shape class. When inspecting a shape, we can use a combination of the alternative pattern and the compound pattern to both determine whether the shape is a circle or a rectangle and also decompose it at the same time into its defining characteristics. Alternatives can also be useful when working with dependent types in a template, as we'll see a little later. Extractor patterns allow us to completely customize matching and decomposition by implementing our own extractor protocols. An extractor is an object that has either an extract or try-extract method. When an extractor pattern is used, this method is called with the value under inspection, and then if the result of that call has a value, it is matched against the child pattern. For example, in the first pattern in this inspect, phone number.tryExtract will be called, and if it returns a value, that value will be matched against the compound pattern here. Now let's look at a more detailed example that combines the power of pattern matching with reflection. We're going to write a simple function to serialize C++ objects to JSON. So our function will take an object that we want to serialize, and it will return a std string. First, we create the string that will fill with the JSON. We add an opening brace to it, which will close at the end of the function after we've filled it with content. We'll get a vector of meta info listing all of the non-static data members of the thing that we're reflecting upon. And we'll iterate through it with a template for, and we'll output the name of each member first using meta name of. And then we inspect the member to output its value. So if it's something that's convertible to a string, then we output it in quotes. If it's a range, we recursively call save.json on each element of the range, and then use std_format's default range formatting, which happens to output a JSON list. If it's a pointer and that pointer is equal to null, then we output null, which is a JSON constant. And if it's a non-null pointer, we just output its address. If the member satisfies the numeric concept, you can match on a concept as well, then we output it as a number using the default formatting. And if it's a bool, we output either true or false, as those are constants in JSON. And then finally, if the member is something else, we just recursively call save.json on it. And then we add a comma after the member unless it's the last member. And then finally, after we've done that for each of the members and added a closing brace, we return the string. And so that's it. In just a few lines of code, we've written a powerful and generic serialization function using pattern matching and reflection. Now, writing this today would be a lot more verbose and would likely require each type to opt in and provide its own serialization function. So inspect gives us a powerful new way to select and decompose objects. It makes working with tuple-like and variant-like objects far more natural in C++. And I think it will revolutionize how we write C++. It'll make it a lot easier to express conditional logic and control flow. These are sea lions. They're quite tired, just like you will probably be after this talk. But don't worry, we are nearing the end. I think there's 4 of them there. So finally, let's talk about asynchrony in C++. Today, C++ has no standard model for asynchrony and no standard way to express where things should execute. And that's why we're introducing senders, a model for asynchronous execution in C++. And there are 3 key concepts in the senders model. Schedulers are lightweight, non-owning handles to execution contexts. Schedulers produce senders, and senders represent asynchronous work that will eventually send a signal. Now, a signal is either success and a set of values produced by the work, failure and an error produced by the work, or cancellation. Senders can be composed together with sender algorithms to form task graphs. Now, receivers are connected to senders and process their asynchronous signals. So let's look at a simple example. First, we need to get a scheduler from somewhere. This could be a thread pool, it could be some sort of lightweight tasking system, it could be a GPU driver, etc. To start a chain of work on the scheduler, we call schedule on it, which returns a sender. That sender will complete on the execution context associated with the scheduler. It doesn't do any work. It's just a handle to start a chain of work. Next, we use a sender algorithm, then, to compose work onto the sender that we got from the scheduler. And this work will then be performed on that same execution context. The sender algorithm will return a new sender, which we can use to add more work onto the chain. Finally, we wait until the chain of work is completed using sync wait, which will return the value sent by the final sender in the chain. Now, most sender operations are pipeable just like range adapters. So the semantics here are similar to Unix shells. Send pipe F pipe G is equivalent to G of F of send. So languages like Haskell and APL call this point-free style. The primary input argument is not explicitly named. So this syntax is essential for elegant composition of senders. This pipe syntax gives us a clean way to compose chains of senders together in the order that they will be evaluated. So let me show you some of the most important sender algorithms that you should know about. Sender adapters are a type of sender algorithm that take one or more senders as parameters and return a sender. So they're the chainable part. Then takes an invocable f and calls it with the values sent by the prior sender. The sender returned from then will send the results of the invocation of f. So this is how you attach a continuation to a sender. Bulk is similar to then. It evaluates the invocable once for every index up to n. So this is how you do parallel work, for example, parallel work that you might want to run on a GPU or on some set of threads. The sender returned from bulk will just pass along any sender signals that were sent by the prior sender. Transfer changes the scheduler that will be used for the next sender. So it doesn't change anything about work before it in the chain, but it says switch to this scheduler for anything that gets added after me. Now, some senders can only be connected to a single receiver. For example, because they move any values or errors that they send instead of copying them. And we call these one-shot senders. Senders that can be connected multiple times are called multi-shot senders. Split will take any type of sender, and it will return a multi-shot sender that passes along the signal from the original sender. So it will, if needed, it will create some shared storage somewhere. It'll have the original input one-shot sender right into that shared storage, and then as many things as want to can connect to that shared storage. So split senders represent forks in a sender task graph. Conversely, when all takes multiple input senders and returns a single aggregate sender that will send the signals from all of those inputs. Now, senders returned by WinAll do not have a scheduler associated with them, which means they do not promise where they complete. WinAll senders represent joins in a sender task algorithm, in a sender task graph. Now, WinAll is not a pipeable sender adapter because it takes an arbitrary set of senders. So if it was pipeable, it would be ambiguous about whether you meant for this to be a partially applied form or whether you meant for it to be just these set here. Now, ensure started connects and starts a sender, returning a new sender that will pass the signal sent by the original. If the input sender is a composition containing other senders, those senders will be connected and started as well. The sender model is default by lazy. Stuff doesn't start running until you have connected it somewhere. Sender factories are another kind of sender algorithm. They do not take senders as parameters, but they do return a sender. So sender factories are used to start new chains and graphs. The senders they return are the root nodes. And we've already seen one sender factory, which is schedule. And that returns a sender that will complete on the specified scheduler. And that return sender doesn't send values or represent any actual work. As I said before, it's just a handle that you can use to compose work on that scheduler. Just is another sender factory. It takes a set of values and produces a sender that will send those values immediately when connected. So just takes, a T and produces a sender of a T. It's a way of going from the synchronous world to the asynchronous world. The last type of sender algorithm are sender consumers. So these take senders but do not return senders. So they typically will launch a sender graph by connecting and starting it. So they are the leaf nodes of sender graphs. Sync wait is a sender consumer and synchronization primitive that blocks until a sender completes and then returns or throws whatever was sent. So we've developed a prototype of senders at NVIDIA that supports CPU schedulers, GPU schedulers, and distributed schedulers. It's available in our NVIDIA HPC compiler. And here's an example from our implementation. This is a simple electromagnetic wave simulation that solves Maxwell's equations on a uniform grid. This is the entire solver loop, which is expressed as a graph of senders. This repeat sender here is just sort of a looping construct. So this code can be run with a variety of different schedulers. By changing just one line of code, the kind of scheduler passed to the solver, we can go from running inline on a single CPU thread to running in parallel on a CPU using OpenMP, to running on a single GPU, to running on multiple GPUs within a single node, and to multiple nodes scaling up to thousands of GPUs, all with standard C++, all in a portable fashion. So we've ported a simulation from the Plabos fluid dynamics framework to senders. This simulation models carbon sequestration techniques. The porous structure that you see is sandstone that is saturated in salt water. And the red bubbles are liquid CO2, which is injected at the bottom. It'll loop around in a moment or so, and travels through the sandstone because of buoyancy forces. Using a distributed GPU scheduler, we've been able to run this application on up to 512 GPUs. With standard C++ senders, you can change one line of code and scale from a single CPU thread up to an entire cluster of GPUs. A growing number of HPC projects have discovered the productivity and performance advantages of using C++ standard parallelism, and I could really only cover a handful of them in this talk. If you're interested in seeing more examples, here are some excellent open source projects using C++ standard parallelism that you can download and study today. I've also given a number of talks on this with the conveniently easy to find title C++ standard parallelism. Now let's look at an example of senders from the networking world. So we're going to do an asynchronous read of an array of data of unknown length. So we'll use this dynamic buffer type to store the data we read in a unique pointer, as well as the size. So our asynchronous read array function will return a sender which will send one of these dynamic buffer things. It will take a handle to whatever networking library we are working with. We'll start our sender chain by introducing a new dynamic buffer object with just. Next, we'll use a letValue sender adapter to create a scope, which will keep the buffer alive for as long as we need it. Now, the first thing we need to do is figure out how big the array will be. We'll expect that sender will send a size t that contains the size of the rest of the data. So we'll need to read that size t first. So we get a span to the size member of this dynamic buffer object. And then we call async read a sender adapter that expects a span and reads into it. Async read will send the number of bytes that it read. So we'll add a then, which is going to do 3 things. First, we will make sure that we read the number of bytes that we expected, which is a size t's worth. Next, we will read the size and allocate a buffer of the specified size, storing it in the unique putter. And finally, we will return a span to that storage. Now we're ready to do a second async read, which will read the actual data. After that read, we have a second then, which will confirm that we read the number of bytes that we expected, which is the actual data of the array. And then with that, we are done. And we will return the buffer from this function via the sender, and somebody else can go use it. So let's look at another example, a generic asynchronous and parallel inclusive scan implemented with senders. So it's going to take 3 parameters, a sender, which we'll expect to send the input as a range, an initial value, which will be an immediate, and the number of tiles to split the input into. We're going to use the classic 2-pass parallel scan approach, which is work efficient, but not the fastest, but it is the simplest for us to show. So this requires temporary storage for partial results communicated between tiles. So we need to allocate this temporary storage asynchronously once the prior sender has sent us the input. The size of the temporary storage depends on the input, so we can't do it before then. So we'll chain a then sender onto the prior sender. In the body of this continuation, we'll create a std vector to hold the partial results. And then we'll return both the input range and the vector that will be sent on to the next thing in the chain. Next, we need to do the first parallel pass called the down sweep. We'll use bulk to invoke the body of the pass for each of the tiles. The first thing we do for each tile is calculate the range of elements that belong to the tile. And then we take all of the elements in each tile and we perform a local serial inclusive scan on them, which we do right here in the code. Next, we need to propagate information between the tiles. So the sum of each tile needs to be added to the elements of all subsequent tiles. We've already computed that sum. It's the last element of the local inclusive scan. We store that result into the partials vector. And assignments to partials from different tiles may happen concurrently, but that's perfectly fine. Each tile uses a different and unique slot in partials, and no one reads from partials yet, so there's no data race here. Then, after all the tiles have completed their local inclusive scans and written to partials, we need to have one execution agent do a serial scan of partials. We do this by piping another then sender onto the chain, which will perform the partials inclusive scan. This then sender will again pass along the input sequence and the partials vector. The result of the scan over partials looks like this. And as you can see, the information that each tile needs to add to its elements is in the partials slot for the tile directly preceding it. So now we need to go parallel again to distribute that information within all of the tiles, and this is called the upsweep pass. So we'll pipe another bulk, once again over all tiles, and in the body of this bulk, we'll need to calculate which elements belong to the current tile, just as we did before in the downsweep pass. And then we use a serial for each to increment each element in the tile by the appropriate correction value from the partials vector. And after that addition, we'll have the correct result. So for every element of the output, we have the partial sum up to that element. Finally, we want the sender returned by our asynchronous inclusive scan to only send the input sequence, not the partials vector. So we add a final then sender, which only passes along the input. And then the partials vector will be destroyed when this then sender completes, which is what we want because it was temporary storage that we want to go away. But we don't want it to go away too early. And that's it. We are done. We've got a generic, asynchronous, and parallel inclusive scan that we can run on any scheduler we want and at any scale that we want, from a small embedded device on a single thread to thousands of GPUs, just by changing the scheduler. And it's all standard C++. So, reflection, pattern matching, and senders. I believe that these are the three most exciting C++ features that we're working on. And combined, they'll radically improve how we express ourselves in C++ and allow us to elegantly solve problems that are challenging today. And as I mentioned, senders has already been voted into C++ 26. It's like 99.9% chance that it will make it in at this point. For it to not be in C++ 26, the committee would have to agree to take it out, which is very, very rare. Reflection has been design approved for C++ 26, which is really the hard part. Now we just have to finalize the specification, make sure that no new big design questions arise in getting the specification completed, and then we'll vote it in probably sometime in the next 3 to 6 months. The part of reflection that's going to be shipping, though, is just a core proposal. It does not include token sequences. We're still hopeful that we'll get token sequences and things like queue injection in, but those may come later. So finally, I'd like to thank everyone who's worked on the features that I've discussed in this talk or otherwise helped me prepare this material. And I'd like to thank all of you for your time and attention. And feel free to contact me if you want to learn more about standard C++ or get involved in the development of C++. You can also check out my other talks. I neglected to mention earlier, if you're interested in learning more about parallel algorithms like that inclusive scan that I showed, I have a whole talk on it called Think Parallel. You should also check out my podcast, ADSP, available on all streaming platforms. These are penguins, Galapagos penguins. They live at the equator, even though they're penguins. It's pretty cool. And these are albatrosses that are performing their mating dance, which is how they know how to find their mate again when they reunite every year. So, questions? Yeah, I got one in the back. No, the extractors, for pattern matching, the question is, do the extractors need extractor in the name? No, an extractor can be called whatever you want it to be called. The way that you know that it's an extractor is just that it inherits from some type that indicates that it's an extractor, and then you use it in the extractor pattern syntax, and then there's a protocol by which the pattern matching machinery understands that this thing's an extractor. We can take a look. So yeah, we have phone number extractor here, the struct, and then we create an instance of it, a context per instance of it. And then it's the question mark says this thing's an extractor. And no, I guess I was wrong, that there's not actually, you just have to implement the protocol. You don't have to actually inherit from any class or anything. It knows that it's an extractor because you use it with the special extractor pattern. Any other questions? Yeah.
Maybe a vague question, but regarding pattern matching, I know that Sean Baxter implemented it in Circle, and this one is not yet planned for standardization.
Nobody's working on it for standardization. So that's why it's not making progress.
Are there different implementations that are occurring?
I don't know because nobody's currently working on it. There haven't been, like, to my knowledge, there haven't been updates in the last couple of committee meetings. Whereas things like reflection and senders are things that there's people driving it and there's progress being made on it every meeting. Right now, there's not people championing pattern matching, or the people who are championing it don't have the cycles to be able to do big major updates every meeting, which is why it's not progressing.
Do you have an opinion on Circle compared to this?
I mean, Circle's a different thing. Circle's great, but it is not open source. So I think it's very hard for Circle to get the sort of adoption that it would need. I think Circle is a far better compiler than most of the C++ compilers out there. Circle is like 10 years ahead of all the other compilers, and Sean is able to move faster than all the other compilers, which is both speaks to Sean's quality as a person and also is an indictment of the state of C++ compilers. However, the path forward for something like Circle is unclear because we don't have somebody proposing to put the Circle features into the standard, and the implementation isn't open source, so people aren't willing to adopt it. So for right now, it remains an amazing technology that nobody's going to put into production. Other questions? Cool. Everybody asked questions about the middle feature, the one that we're least likely to get. All right.
Most easy to comprehend.
It is probably the most easy to comprehend. Reflection used to be a little bit simpler, but now it's not. Okay. All right, I'll be around the rest of the day, and tomorrow come find me if you're 2ShotX questions during the session itself. Thank y'all.